What happens when you match one of these natural frequencies of a system externally? What that means is you're generating an external wave and you're creating some kind of an interference pattern, the constructive interference pattern with one of those natural frequencies. Natural frequency that you match with is the one that you're going to get to amplify, which means that you cause a constructive interference pattern, and when there's a constructive interference pattern, that vibration's amplitude is going to get maximized.
Just like this.
So these people are crossing their legs.
American is proud to be the only airline to
at a frequency that matches one of the natural frequencies of this airplane.
remove seats throughout coach, so you all can
So the amplitude of that frequency is getting
have
maximized.
more room to cross your legs. However, we do kindly request that you
All right, so the amplitude in this case represents the disturbance with respect to the undisturbed position of these airplanes.
all do.
So it's just going to go up and down as you start to feed more and more energy in it. So what happens, the amplitude is going to get larger and larger and larger until the system reaches its physical
But at
breakdown.
the same time,
That's what happens with the mechanical systems usually. All right, so the only thing you have to do is match one of the natural frequencies of the system by an external
All right,
wave.
the time has come to break the wine glass. But I'm not going to do it with my own voice. My contract with the Met won't permit that. And there's another problem. This takes practice, and I only have the one wine glass. So I'm going to try it first using this ordinary laboratory beaker. Now here's how it's going to work. All of this stuff here is going to substitute for me and make a pure tone. That'll make the beaker vibrate. And then I've got this microphone here which is listening to what the beaker does. And the output of the microphone is on this oscilloscope, so you'll be able to see on the oscilloscope what the beaker is doing. Watch this. You see that? Okay. Now, what I have to do is to turn up the volume, and that makes the beaker vibrate. Now you can see that the beaker is vibrating, but not very much because it's not exactly at the right frequency. It has to be at precisely the right frequency, the resonant frequency of the beaker, in order to vibrate enough to make it break. So I'm going to tune this to the right frequency. There it is, right there. That's it. All right? Now all I have to do is to turn up the volume all the way up, and it'll break the beaker. Okay, you ready for this? And the people in the first couple of rows, your ears will bleed a little bit, but don't worry about it. It's not serious. You ready for this? Here we go. So we managed to do it without ever breaking this exquisite wine glass. You see, that's why they bought it for me. They knew I'd never get around to breaking it. All right? That's it for today.
Okay, so whenever you match the natural frequency of a system, you're going to be able to increase its amplitude. All right, so this thing's got its own natural frequency. It's going to move like a pendulum on its own. So if I were to start reinforcing this frequency, what happens is the amplitude is going to get larger and larger. All right, so you pick one of the natural frequencies, fundamental frequency, or it's one of its multiples, and if you start reinforcing that frequency by a frequency, external frequency that matches that frequency, it causes a constructive interference pattern, so the amplitude is going to gradually start to increase, and the system reaches its breaking point. All right, so this brings us to the next point.
With a span almost was the most famous bridge in
an old-fashioned elevator. Boom, like that.
Galloping Gertie remained open to traffic for 4 months, but in November everybody was ordered off as a 40-mile-an-hour gale whipped across her deck, lifting the roadway like a sail.
All right, so what happened to the bridge?
We went out to watch it whip,
It resonated.
and it was really whipping.
It came down because of resonance.
And there was one car on it. But then it got late, and so we left.
By afternoon, the stresses were too much. Incredibly, the 11,000-ton center span ripped away and crashed into the sea. Aerodynamic problems had never been considered important before.
Guys, you got a wind which is about 40 mile per hour gust. So how did that create waves on the bridge?
Every bridge ever
What happened there?
designed, even the smallest arch over a stream, has some aerodynamic lift associated with that span, some aerodynamic characteristics.
Oh. What's happening with the bridge that brought it down, if that's the case?
State opened in 1940 with science. On the other coast, New York's spectacular gold.
Okay, let's take a look at the bridge. What's the problem with the bridge? All right, another thing that you were supposed to do, which I'm not going to cover because I have no use for it this semester. I'm not going to review that for you guys, is the fluid dynamics. All right, so if the wind is coming across the bridge, part of the air is going to go under, part of the air is going to go over the bridge. So the question is, which part is moving faster, the part going under the bridge or over the bridge? What do you guys think? So the air is going to split, the wind is going to split, part of it is going to go under, part of it is going to go over. So which part of the wind is moving, which portion of the wind is traveling faster? Portion going over the bridge or under the bridge?
Probably over.
Okay, Nathan, why did you say over?
Golden Gate
There's a bunch of trusses and stuff underneath. They'll probably block the flow and make it.
Bridge in San Francisco.
Okay, let's put it this way. The water coming out of a partially closed hose, why does the water come out faster? It's called the constancy of the mass flow rate, right? All right, which means that the amount of water going in and coming out of the contraption has to be the same, which means that when fluids are forced into a smaller opening, they will speed up. That's what it means. All right, so air is also a fluid. Fluid doesn't mean that it needs to be wet. It can be wet, but it doesn't need to be. It simply means that it is capable of flowing. Anything that flows is known as a fluid. So what do we know from that analogy? We know that when the fluids are forced into a smaller opening, they will just speed up. Notice that the space underneath is smaller than the space above. So which means that the air moving underneath is going to move faster. So what happens when the air is moving faster? It creates a lower pressure. All right, so which means that the bridge is going to get pulled down. And then the structure is going to bounce up. It's going to get pulled down again. It's going to bounce up again. It's going to get pulled down. And then it's going to get bounced up on its own. All right. So that frequency, if it matches one of the natural frequencies of the system, that frequency is going to get amplified. So that's what happened to the bridge. So what was wrong with the design? It wasn't the design characteristics. The bridge looked fine. The bridge looked like it was supposed to. All right. It was a cute looking bridge. Oh my God, look at my design of the bridge. Okay, so a couple of things that you could fix regarding the bridge. The bridge resonated, and you don't want any sort of resonance in the bridge. So a couple of things that you need to fix about the bridge. Number one, you can change the length. So it's going to reduce the natural frequency of the bridge. What's the problem with that? If you increase the length, you cannot make it any shorter, but you can just definitely increase the length. If you increase the length, what's going to happen is the natural frequency is going to go down. If it goes down, it can be much more easily matched. I mean, you're on this bridge, you're far on this bridge, the bridge is going to come down. All right, you don't want that. You cannot make the natural frequencies of a bridge really, really low. That was part of the problem. All right, so you cannot change this length, so that's out of the question. What is it that you can change? You can certainly make it heavier. All right, so you can make it heavier. If you make it heavier, once again, you got the same problem. Natural frequency of the bridge is going to be way too low, so which means that you can match it easily externally. A 48-mile-per-hour gust is going to bring it down. You don't want that. So what's the only thing that you could do? Increase the tension, guys. The best thing to do is increase the tension. What does it mean? Just make it more rigid. Oh my God, just make it more rigid. The first time you saw that, you know that's got a problem, right? This thing is swinging all over the place, all right? These people, after all the math, all the physics, and all the engineering, they didn't realize that just make it much more rigid. Today, this is known as engineering proof. This is known as the earthquake proof engineering. Earthquakes generate known frequencies. So whenever you build something, you make sure that none of the earthquake frequencies can match any of the natural frequencies of a building, guys. All right, that's the way it is done usually. I'm very surprised that the civil engineers in building these bridges, they still repeat the same sort of mistakes. So in order to prevent that from happening, they put dampers all over the place. All right, that's one of the ways of preventing that from happening.